Hello and welcome to this new lecture. In this lecture, we'll talk more about the speed of sound, and we will try to prove the following relationship, that the speed of sound c is equal to the square root of the bulk modulus of elasticity b divided by the density rho. So to do this, we will take a channel. So inside this channel, we have a fluid at rest having a velocity equal to 0, pressure p, and a density rho. And at some location inside this channel, we will create a very small disturbance. So maybe this disturbance is created by a loudspeaker, for example, or a very tiny explosion. So this small disturbance will create a pressure wave inside this channel, and this pressure wave will be propagating at the speed of sound c. So to the left of this pressure wave, the fluid will experience a change in its properties. So for example, the pressure will be P plus a differential change dP. The density rho will be equal to rho plus d rho. And also, this pressure wave will cause the fluid to follow at a velocity, at a differential velocity equal to dV. Now, why we're talking about only a differential change, dP, d rho, and the differential velocity, dV? Since here we're considering a pressure wave that has infinitesimal strength, since this pressure wave is created by a very small disturbance. So that's why this pressure wave will only cause a very small change in the fluid properties. Now what we want to do a control volume analysis. So to simplify our analysis, we will take a control volume surrounding the pressure wave, and this control volume is also moving at the speed of sound c. So for an observer located inside this control volume, the pressure wave will appear still, not moving, or fixed, if we want to say. And for this observer, it will appear to him as if the fluid is moving toward the control volume at the speed of sound c. And also it will appear to him as if the fluid is exiting the control volume at a speed equal to c minus dv, since if you look at the initial sketch here, this pressure wave will cause the fluid to move to the right at the differential velocity dv. So that's why from this observer point of view, it will appear as the fluid is moving or leaving the control volume at a reduced velocity, which is equal to c minus dv. And of course, let's not forget that the properties here will be p plus dp, the density is rho plus d rho, and to the right of this control volume, we have the pressure p and the density rho. Now let's apply mass conservation on this control volume. So at steady state, the mass flowing into the control volume will be equal to the mass flow rate flowing out of the control volume. So the mass flow rate flowing in is simply equal to rho into the frontal area, so this frontal area, multiplied by the flow velocity, which is c, which is equal to the mass flow rate flowing out, which is the density, the new density, rho plus d rho, into the frontal area A, into the exit velocity, which is c minus dv. Now let's simplify the area from both sides. We will have rho c is equal to rho c minus rho dv plus c d rho minus d rho dv. So you can notice here we have a second order term. So second order terms can be neglected. So this is the multiplication of two differential quantities. Now we can simplify rho c with rho c. We'll have rho dv is equal to c d rho, and now dv is simply c d rho over rho. So this is our first equation obtained from applying the mass conservation on the control volume. Now we will apply next the linear momentum equation, the linear momentum on this control volume. So from fluid mechanics courses, if you took any fluid mechanics courses, you know that summation of forces acting on a control volume is equal to the mass flow rate multiplied by the exit velocity vector VE minus the inlet velocity vector VI. Now, what are the forces acting on this control volume? So, as we saw, we have the pressure wave here, the control volume surrounding the pressure wave. We have a pressure distribution to the left of this control volume, and we have the pressure P plus dP. And to the right of this control volume, we have a distribution of a pressure with a value equal to P. And of course, here we will neglect any shear stress where we have a contact between the control volume and the wall of the channel, since the thickness of this pressure wave can be assumed to be negligible. The thickness of this pressure wave is in the order of 10 minus 6. So any frictional forces due to this stress distribution can be neglected. So we can assume a frictionless flow. Okay. So the only forces acting on this control volume are due to the pressure distribution. Now let's project this equation by assuming that to the right is positive. So we have P plus dP into the area minus the pressure into the frontal area. So why we have this minus sign? Of course, because the pressure here to the right is acting to the left of the control volume, and we're assuming that to the right is positive. Okay. Now this is equal to the mass flow rate. The mass flow rate, we have the mass flow rate at the inlet and the mass flow rate at the exit. So it is easier to choose the mass flow rate and at the inlet. Okay, since this is simply equal to rho AC multiplied by the velocity vector at the exit. So this is the velocity vector at the exit. And you can see that this velocity vector is pointing to the left and having a magnitude equal to C minus dV. So since this is pointing to the left and we're assuming to the right is positive, we need to put a minus sign. So minus C minus dV minus the velocity vector at the inlet of the control volume. So this one here, and it is also pointing to the left and it has a magnitude equal to C. So since it is pointing to the left, we need to put minus C. Now let's simplify all the areas here, and let's P with minus P will be eliminated, and we will have dP is equal to rho C into minus C plus dV plus C. So C with minus C also will be eliminated, and we'll have dP is equal to rho C dV. And as a result, we have our second equation where dV is simply dP over rho C. So this is our second equation. Now what we want to do, we will put the second equation into the first equation. So we will replace this dV here by dP over rho C. So we'll have dP over rho C is equal to C d rho over rho. So C d rho over rho. We simplify rho from both sides, and we will have C square is equal to dP over d rho. And as a result, the speed of sound C is square root of dP over d rho. Now, how to relate this to the bulk modulus of elasticity? We saw in the previous lecture that the bulk modulus is simply equal to dP over d rho over rho, and we can write it in the following form: rho into dP over d rho. So simply dP over d rho is the bulk modulus divided by the density. So we can replace this dP over d rho by B over rho. So C now will be equal to the square root of B over rho. So this is our proof for this equation. And you can use this equation if you want to calculate the speed of sound in solids, liquids, or in gases. So simply, if you know the bulk modulus of elasticity and the density rho, we use this equation to calculate the speed of sound. Now, what we want to do, we want to further expand our analysis by dealing with ideal gases. So ideal gases. So we want to obtain an expression for the speed of sound for ideal gases. And we know that first the ideal gas law, PV is equal to RT, where V is the specific volume. However, this form is mainly if you're talking from a thermodynamic point of view. However, in fluid mechanics, we like to write this ideal gas law by using the density rho instead of the specific volume. And we know that the density rho is simply the inverse of the specific volume. So this ideal gas equation will be simply P is equal to rho RT. So this is the ideal gas equation. Another important relationship is called the polytropic relation. So the polytropic relation, we have PV to power n is equal to a constant. Now this value of n can be different regarding which is related to the type of the process. For example, if you take n is equal to 0, you will have P is equal to a constant. Simply V to power 0 is 1, and you will have P is equal to constant. And this process is called an isobaric process. So an isobaric process is a process where the pressure is constant across this process or along this process. If you take n is equal to 1, you will have PV is equal to constant. So n is equal to 1, you will have PV is equal to constant. So when PV is equal to constant, this simply means that this process is happening at constant temperature. And we call this process an isothermal process. An isothermal process. Okay? And the last one that I want to talk about is when n is equal to K, where K is the specific heat capacity ratio, which is the specific heat Cp at constant pressure divided by the specific heat Cv at constant volume. So when n is equal to K, we'll have PV to power K is equal to a constant, and this process is called an isentropic process. An isentropic process. So a process happening at constant entropy. So why we're talking about these types of processes? Because if we look at the expression of the speed of sound, C, which is the square root of dP over d rho. So we need to differentiate the pressure with respect to the density. So to do this, we need a relationship relating the pressure to the density. And this relationship should be given by one of these processes. So we need to assume a type of a process for this problem. So either our problem can be considered an isobaric, isothermal, or isentropic. So the best assumption here is to consider the process as isentropic. Why? Because as we said, since the pressure wave here, the sound wave is very thin, and as we said, it is in the order of 10 minus 6 in thickness, it means that the frictional forces with the wall can be considered negligible. So this is a frictionless process. And also, due to very small temperature variation, we can assume that the process is adiabatic also. So there is no heat transfer between the control volume and the surrounding. So, and we know from thermodynamics that the combination of the two conditions, so frictionless plus adiabatic, simply means isentropic. So frictionless, in other words, we call it reversible. So maybe mainly irreversibilities can be caused by frictional effect. And since here we have a frictionless process, this means that this process is free of irreversibility, and we call it reversible. And adiabatic simply means that heat transfer is negligible. So negligible. And the combination of these two conditions is called an isentropic process. So let's go back. When we have isentropic process, it means that PV to power K is equal to a constant. And in terms of the density, we can say this is P over rho to power K is equal to a constant. And now the pressure will be equal to the constant into rho to power K. Now, let's differentiate this equation. We'll have dP is equal to the constant into K rho K minus 1 d rho. So now dP over d rho for this isentropic process is constant into K rho K minus 1. So what is this constant? So we can replace this constant by this expression, which is the pressure over rho to power K. So we can write it P over rho to power K into rho to power K minus 1. So rho to power K minus 1 divided by rho to power K is simply rho to power minus 1. So we'll have dP over d rho is equal to P into rho to power minus 1, or we can say divided by rho into K. And also, as we said, the ideal gas law, P is equal to rho RT. So P over rho in this case is RT. So we replace this here by RT, and we will have that the derivative of P with respect to rho is simply KRT. So this is only valid for an isentropic process. And let's go back to our C, the speed of sound expression. So the speed of sound is simply the square root of dP over d rho. So this means that dP over d rho is simply c squared. So the speed of sound in ideal gas will be equal to the square root of kRt. So this is our expression for the speed of sound in ideal gases. And we can use this expression to calculate the speed of sound C. And you can notice here that the speed of sound is proportional to the square root of the temperature. So for example, if you want to calculate the speed of sound at very high altitudes, where the temperature of air is really low, you will obtain lower values of speed of sound when compared, for example, at sea level. So at sea level, the temperature will be higher, and as a result, the speed of sound will be higher. So let's give some examples. Let's start with water, for example. Water at a temperature of 20 degrees Celsius. So at a temperature of 20 degrees Celsius, the bulk modulus of elasticity for water will be equal to 2.19 gigapascal, and the density of water will be 998 kilograms per meter cube. So the speed of sound C is the square root of 2.19 times 10 to power 9 to convert it to Pascal divided by 998. So the speed of sound will be approximately 1481 meters per second. So this is a very large value, very high velocity. Now, let's compare it with air at the same temperature, at a temperature of 20 degrees Celsius. So for air, the specific heat capacity ratio K is simply 1.4, and the gas constant for air is 287 joule per kilogram Kelvin. So using this relationship, you can find the speed of sound in air, which is square root of K into R into T. The temperature should be in Kelvin. So here we have 20 degrees Celsius, which is 293 Kelvin. So this is approximately equal to 343 meters per second. And you can see that the speed of sound in air is smaller than the speed of sound in water. And in general, the speed of sound in gases is much smaller than the speed of sound in liquids. Because if you want to look at it in this way, in liquids, the molecules are much closer to each other. So as a result, the molecules will help transport the vibrational energy at a faster rate when compared to gases. And we know that the particles, in gases are much more widely spread, and as a result, this will slow the transport of the vibrational energy, which is the pressure wave, if we want to say. So, if we want to go back to our incompressible flow criterion, we said that for incompressible flow, the Mach number should be less than or equal to 0.3 to consider incompressible flow, or in other words, to neglect compressibility effects. And so obviously, if the speed of sound is lower, we can reach this condition much easier. So this condition is very hard to reach when we're talking about a flow of water, for example, when compared to flow of air. So let's say we have a commercial airplane. So let's talk about a commercial airplane flying at some altitude equal to 9 kilometers, where the temperature of air at this altitude is minus 44 degrees Celsius. So the speed of sound at this altitude will be equal to the square root of K into R into T. So in Kelvin, this will be 229. So the speed of sound will be 303 meters per second. And commercial airplanes mainly, for example, will travel at a velocity equal to 900 kilometers per hour, or in meters per second, this will be equivalent to 250 meters per second. So if you calculate the Mach number, which is V over C, so for this commercial airplane, the Mach number will be equal to 0.8. So you can see in practical applications, the Mach number can easily be greater than 0.3, and here, which is the case, and we can say that compressibility effects cannot be ignored, so they are important. Okay, so as you can see here, we have developed an expression to calculate the speed of sound in ideal gases, and in the next lecture we will talk about the stagnation properties. So let's see about the stagnation properties in the next lecture, and I hope that you like the lecture so far, and please don't forget to leave a review. So see you in the next lecture.